Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Computer and Information Sciences, SOCIS, Postgraduate Diploma in Computer Applications, PGDCA, New, Semester 2, MCS207 Database Management Systems, Block to Database Normalization and Database Query, Unit-5 Database Integrity, Functional Dependency and Normalization, 5.0 Introduction. The first block of this course discusses the database concept, relational algebra, entity, relationship, model and integrity constraints in the context of relational database design. One of the key aspects of database design is to create relations without any data redundancy. This unit first explains the concept of entity and referential integrity. It also explains the anomalies in a relational database system. To remove anomalies is through decomposing the database. You need to decompose relations into smaller relations, which are free of those anomalies. This decomposition may be lossless and dependency preserving. The unit explains the concept of functional dependency, which is the basis of lossless decomposition of a relation into smaller relations. The unit deals with the standard form of database relations and discusses the process of decomposing relations into different normal forms up to BCNF. The higher normal forms are discussed in the next unit, 5.1 Objectives. After going through this unit, you should be able to times explain entity integrity and referential integrity constraints of a relation, times explain various anomalies that exist in a database system, times define the desirable properties of decomposing a relation, times define and use functional dependencies to normalize databases. 5. Normalization. Point to database integrity. Database integrity refers to maintaining the consistency of data in the database. Data integrity relates to the correctness of data and often is implemented using constraints on attributes in one or more relations. In this section, we will discuss more about two important integrity constraints of a database, the entity integrity constraint and the referential integrity constraint. To define these two, let us once again define the term key with respect to a database management system. 5.2.1 The keys. Candidate key. In a relation R, a candidate key for R is a subset of the set of attributes of R, which have the following two properties. 1. Uniqueness. No two distinct tuples in R have the same value for the candidate key. 2. Irreducible. No proper subset of the candidate key has the uniqueness property. Every relation must have at least one candidate key which cannot be reduced further. Duplicate tuples are not allowed in relations. Any candidate key can be a composite key also. For example, student ID course ID together can form the candidate key of a relation called result, student ID, course ID, marks, dot. Let us summarize the properties of a candidate key. Times a candidate key must be unique and irreducible. Times a candidate may involve one or more than one attribute. A candidate key that involves more than one attribute is said to be composite. But why are we interested in candidate keys? Candidate keys are important because they provide the basic tuple-level identification mechanism in a relational system. For example, if the enrollment number is the candidate key of a student relation, then the answer of the query, find student details from the student relation having enrollment number 0, 1 to 3, will output at most one tuple. Primary key. The primary key is the candidate key that is chosen by the database designer as the principal means of identifying entities within an entity set. The remaining candidate keys, if any, are called alternate keys, foreign keys. Let us first give you the basic definition of foreign key. Let R to be a relation, then a foreign key in R2 is a subset of the set of attributes of R2, such that 1. There exists a relation R1 and R2 not necessarily distinct, with a candidate key, and 2. For all time, each value of a foreign key in the current state or instance of R2 is identical to the value of candidate key in some tuple in the current state of R1, the definition above seems to be very heavy. Therefore, let us define it in more practical terms with the help of the following example. Example 1. Assume that in an organization, an employee may perform different roles in different projects. Say, XYZ is coding in one project and designing in another. Assume that the information is represented by the organization in three different relations named employee, project, and role. The role relation describes the different roles required in any project. Assume that the relational schema for the above three relations are employee, empid, name, designation, project, proj_name, details, role, lead, role_description. In the relations above, empid, project, and role lead are unique and not null. As you can clearly observe, you can identify the complete instance of the entity set, employee, through the attribute empid. Thus, empid is the primary key of the relation employee. Similarly, project and role lead are the primary keys for the relations project and role respectively. Let assignment is a relationship between entities employee and project, and role, describing which employee is working on which project and what the role of the employee is in the respective project. Figure 5.1 shows part of ER diagram for these entities and relationships. For simplicity, no attribute has been shown. Figure 5.1, ER diagram for employee role in development. Look at the screen, figure 5. 2. An example relation. You can define the relational scheme for the relation assignment as follows. Assignment, empid, project, role lead. Please note now that in the relation assignment, as per the definition of foreign key to be taken as R2, empid is the foreign key in assignment relation. It references the relation employee as per the definition to be taken as R1, where empid is the primary key. Similarly, project and role lead in the relation assignment are foreign keys referencing the relation project and role, respectively. Now, after defining the concept of foreign key, we can proceed to discuss the actual integrity constraints, namely referential integrity and entity integrity. 5.2.2 Referential integrity. It can be simply defined as the database must not contain any unmatched foreign key values. The term unmatched foreign key value means a foreign key value for which there does not exist a matching value of the relevant candidate key in the relevant target referenced relation. For example, any value existing in the empid attribute in assignment relation must exist in the employee relation. That is, the only EMPIDs that can exist in the employee relation are 101, 102, and 103 for the present state instance of the database given in figure 5.2. If we want to add a tuple with empid value 104 in the assignment relation, it will cause violation of referential integrity constraint. Logically, it is obvious, after all, the employee 104 does not exist, so how can he be assigned any work? Database modifications can cause violations of referential integrity. We list here the referential action that you may specify for each type of database modification to preserve the referential integrity constraint. Delete. During the deletion of a tuple, two cases can occur. Deletion of tuple in relation having the foreign key. In such a case, simply delete the desired tuple. For example, in assignment relation, you can easily delete the first tuple. Deletion of the target of a foreign key reference. For example, an attempt to delete an employee tuple in employee relation whose empid is 101. This employee appears not only in the employee but also in the assignment relation. Can this tuple be deleted? If you delete the tuple in employee relation, then two unmatched tuples are left in the assignment relation, thus causing violation of referential integrity constraint. Thus, the following two choices exist for such deletion. Restrict. The delete operation is restricted to only the case where there are no matching tuples in the referencing relation. For example, you can delete the employee record of MPID 103 as no matching tuple in assignment but not the record of MPID 101. Cascade, the delete operation cascades to delete those matching tuples also. For example, if the delete mode is cascade, then deleting an employee data having MPID as 101 from employee relation will also cause deletion of two more tuples from assignment relation. Insert. The insertion of a tuple in the target of reference does not cause any violation. However, insertion of a tuple in the relation in which we have the foreign key, for example, in assignment relation, it needs to be ensured that all matching target candidate key exist, otherwise, the insert operation can be rejected. For example, one of the possible assignment insert operations would be 103 LG 3000 dot modify. Modifying or updating operations changes the existing values. If these operations change the value, that is the foreign key also, the only check required is the same as that of the insert operation. What should happen to an attempt to update a candidate key that is the target of a foreign key reference? For example, an attempt to update the project LG for which there exists at least one matching assignment tuple. In general, there are the same possibilities as for delete operation. Restrict. The update operation is restricted to the case where there are no matching assignment tuples. It is rejected otherwise. Cascade. The update operation cascades to update the foreign key in those matching assignment tuples also. 5.2.3 Entity integrity. Before describing the second type of integrity constraint, viz. Entity integrity, you should be familiar with the concept of null. Basically, null is intended as a basis for dealing with the problem of missing information. This kind of situation is frequently encountered in the real world. For example, historical records sometimes have entries such as date of birth unknown. Hence, it is necessary to have some way of dealing with such situations in database systems. God proposed an approach to this issue that makes use of special markers called null to represent such missing information. A given attribute in the relation might or might not be allowed to contain null, but can the primary key or any of its components, in case primary key is a composite key, contain a null? To answer this question, an entity integrity rule states no component of the primary key of a relation is allowed to accept null. In other words, the definition of every attribute involved in the primary key of any basic relation must explicitly or implicitly include the specifications of null not allowed, foreign keys and null. Let us consider the relations dept, ID, name budget. D1 Marketing 10 MD2 Development 12 MD3 Research 5 EMP, ID, name dept, ID, salary, E1 Rohan. D1 40K E2 Aparna D1 42K E3 Ankit D2 30K E4 Sangeeta 35K. Suppose that Sangeeta is not assigned any department in the EMP tuple corresponding to Sangeeta, therefore, there is no genuine department number that can serve as the appropriate value for the depted foreign key. Thus, one cannot determine name and budget for Sangeeta's department as those values are null. This may be a real situation where the person has newly joined and is undergoing training and will be allocated to a department only on completion of the training. Thus, null in foreign key values may not be a logical error, so the foreign key definition may be redefined to include null as an acceptable value in the foreign key for which there is no need to find a matching tuple. 5.3 Redundancy and associated problems. Let us consider the following relation student. Figure 5. 3. A state of student relation. Look at the screen. The above relation satisfies the properties of a relation and contains a single value in each cell. Conceptually, it is convenient to have all the information in one relation, as a single query to the database may produce complete information about a person. Does the student relation as given in Figure 5.3 has any undesirable characteristics, you may observe that Figure 5.3 contains duplicate information in several attributes. For example, the student, whose enrollment number is 050112345 has a name, Rohan, and the student stays at an address D27 Main Road, Ranchi. This information is repetitive in the first three attributes of tuples 1, 2 and 3, shown in Figure 5.3 in red color. Similarly, the information that course name for number MCS207 is OS and it is taught by Preeti Anand, whose office number is 103, shown in Figure 5.3 in purple color. You can observe that even this information is repetitive in tuple 3 and tuple 4. Thus, the relation of Figure 5.3 has the undesirable data redundancy. In addition, when a new student takes admission and enrolls for the course MCS207, then the entire information about the MCS207 will be added to the relation. Such repetitive information not only increases the size of the database, but also results in several problems, which are discussed below. 1. Update anomaly. Consider the data redundancy of student name and address. As shown in Figure 5.3. Assume that the student Rohan shifts from Ranchi to New Delhi at a new address F102 Medan Garhi, New Delhi. This will require updating the address of Rohan in all the three tuples of the student relation. All the three tuples must be updated consistently. If this does not happen, then the address of Rohan will be inconsistent. This inconsistency is the result of update operation on redundant data. Thus, this anomaly is termed an update anomaly, which causes data inconsistency. 2. Insertion anomaly. The note that the primary key of the student relation, as given in Figure 5.3, is composite key consisting of enrollment number and course number. Any new tuple to be inserted in the relation must have a value for both the attributes of the primary key, as entity integrity constraint requires that a key may not be totally or partially null. However, in the given relation, if you want to insert the course number and course name of a new course in the database, it would not be possible until a student enrolls in that course. Similarly, information about a new student cannot be inserted in the database until the student enrolls in a course. These problems are called insertion anomalies. 3. Deletion anomalies. In some instances, useful information may be lost when a tuple is deleted. For example, if you delete the tuple corresponding to student 050111341 enrolled for MCS207, you will lose relevant information about the student with enrollment number, name and address of this student. Similarly, deletion of tuple having student name Rohan and course number MCS202 will result in loss of information that MCS202 is named Computer Organization having an instructor Anurag Sharma, whose office number is 105. This is called deletion anomaly. The anomalies arise primarily because the relation student has information about students as well as courses. One solution to the problems is to decompose the relation into two or more smaller relations so that a relation contains information about one thing. But what should be the basis of this decomposition? To answer the questions, let us try to articulate dependence of data within a relation with the help of the following Figure 5.4. Look at the screen. Figure 5.4. The dependencies of relation in Figure 5.3. In Figure 5.4, an arrow shows dependence of data attributes. For example, you may notice that two arrows, links, are originating from an attribute student enrollment number, sent enroll no. One of these links is to student name attribute, sent name, and the second link to student address, sent address. The link between attribute sent enroll no and student name attribute, sent name, denotes that enrollment number attribute uniquely determines the student's name. For example, in Figure 5.3, the enrollment number 050112345 uniquely determines that name of the student is Rohan. Likewise, you may determine the dependence among different attributes. You may notice that the dependence of data can exist even among the attributes which are not the part of the primary key, such as a dependence from course instructor, co-instructor, attribute to instructor office number, in-office attribute. The dependence among the attributes forms the basis of decomposition of a relation into two or more relations. This is called the normalization. The objective of this decomposition is to reduce the three anomalies in the decomposed relations. However, normalization should not result in loss of information, which means that you should be able to obtain the original relations information by taking join of the relations obtained after decomposition. A relation that needs to be normalized may have a very large number of attributes. In such relations, it is almost impossible for a person to conceptualize all the information and suggest a suitable decomposition to overcome the problems. Such relations need an algorithmic approach for finding if there are problems in a proposed database design and how to eliminate them if they exist. The discussions of these algorithms are beyond the scope of this unit, but we will first introduce you to the basic concept that supports the process of normalization of large databases. So let us first define the concept of functional dependence in the subsequent section and follow it up with the concepts of normalization. 5.4 Functional dependencies. A database is a collection of related information, and it is therefore inevitable that some items of information in the database would depend on some other items of information. The information is either single-valued or multi-valued. The enrollment number of a student and his/her date of birth are single-valued information. Qualifications of a person or subjects that an instructor teaches are multi-valued facts. In this section, we will deal with single-valued facts, which forms the basis of the concept of functional dependency. Let us define this concept logically. Functional dependency, FD. Let us consider a single universal relation schema A. A functional dependency, denoted by XAY, between two sets of attributes X and Y that are subset of universal relation A specifies a constraint on the possible tuples that can form a relational state of A. Consider any two tuples of a relation A, say T1 and T2. A FD is said to exist between two sets of attributes X to Y if the following holds in A. If T1, X, is equal to T2, X, then T1, Y, is equal to T2, Y, must be true. It means that if tuple T1 and tuple T2 have same values for attributes X, then to hold XAY on A, T1 and T2 must have same values for attributes Y also. Thus, FD_XAY means that the values of the Y component of a tuple in A depend on or is determined by the values of X component. In other words, the value of the Y component is uniquely determined by the value of the X component. This is functional dependency from X to Y, but not Y to X. That is, Y is functionally dependent on X. The relation schema A determines the function dependency of Y on X, XAY, when and only when 1. If tuples in A, which agree on their X value, then 2. They must agree on their Y values too. Please note that if XA in A does not mean ya X in A, please note that functional dependency, FD, does not imply a one-to-one relationship between X and Y. For example, the functional dependencies of Figure 5.4 are sent enroll no A sent name, sent address, co-no A co-name, co-instructor. Co-instructor A in office. These functional dependencies imply that there can be only one student name for each, sent enroll no, only one address for each student and only one course name for each, co-no. Please note, given this set of FDs, it is possible that two or more students who have different enrollment numbers may have the same name. In addition, two or more students can reside at the same address. However, two different students cannot have the same enrollment number. Similarly, consider Kono a co-instructor. The dependency implies that no subject can have more than one instructor. Perhaps this is not a very realistic assumption. Functional dependencies therefore place constraints on what information the database may store. In addition, in the example above, you may be wondering if the following FDs hold: sent name A sent enroll no 1, coname A cono 2. Certainly, there is nothing in the given instance of the database relation presented that contradicts the functional dependencies as above. However, whether these FDs hold or not would depend on whether the university or college whose database you are considering allows to different students to have the same name and to different courses to have the same course names. If it was the enterprise policy to have unique course names, then 2 holds. If two students have exactly the same name, then 1 does not hold. Let us use an ER diagram to show various FDs. Please refer to Figure 5. 5. A simple example of functional dependency in this ERD is when X is a primary key of an entity, example enrollment number, and Y is some single-valued property or attribute of the entity, example student name. XAY then must always hold. Why? Functional dependencies also arise in relationships. Let C and D be the primary keys of two strong entity sets participating in a relationship. If the relationship is one-to-many, both the FDCAD and DAC will hold. If the relationship is many-to-one, C, on many side, an FDCAD will hold but the FDDAC will not hold. In case A, relationship cardinality is many-to-many, then the key attributes of the participating entities would not have any functional dependency between them. Figure 5.5 ERD of entities student, course and teacher, identification of FDs. Identification of FDs, in general, is not trivial. You need to study the domain of attributes and relationships among these attributes. You cannot identify FDs by using a set of rules. The following example explains this. Consider the following relation: student course, enroll no, sname, kname, class location, hours. The following functional dependencies may exist on this relation. You should identify the FDs primarily from constraints. There is no thumb rule to do so otherwise. Times enroll no ace name. The enrollment number of a student uniquely determines the student names. Alternatively, you can say that sname is functionally determined dependent on enrollment number. Times class code name, class location. The value of a class code uniquely determines the class name and class location. Times enroll no, class code hours. A combination of enrollment number and class code values uniquely determines the number of hours and students study in the class per week. Hours. The semantic property of functional dependency explains how the attributes in A are related to one another. A FD in A must be used to specify constraints on its attributes that must hold at all times. For example, a FD, state, city, place, a PIN_code should hold for any address in India. It is also possible that certain functional dependencies may cease to exist in the real world if the relationship changes. For example, the FD PIN_code, a area_code, used to exist as a relationship between postal codes and telephone number area codes in India. However, with the proliferation of mobile telephone, the FD is no longer true. The set of FDs over a relation can be optimized to obtain a minimal set of FDs called the canonical cover. However, these topics are beyond the scope of this course and can be studied by consulting further readings. 5.5 Normalization using functional Dependencies, called in the year 1972, presented three normal forms, 1NF, 2NF, and 3NF. These were based on functional dependencies among the attributes of a relation. Later, Boyce and Codd proposed another normal form called the Boyce-Codd normal form, BCNF. The fourth and fifth normal forms are based on multi-valued dependency and joint dependencies and were proposed later. In this section, we will cover normal forms till BCNF only. Fourth and fifth normal forms are discussed in the next unit. For all practical purposes, 3NF or the BCNF are quite adequate since they remove the anomalies discussed for most common situations. It should be clearly understood that there is no obligation to normalize relations to the highest possible level. Performance should be taken into account, and sometimes an organization may take a decision not to normalize, say, beyond third normal form. But it should be noted that such designs should be careful enough to take care of anomalies that would result because of the decision above. Intuitively, the second and third normal forms are designed to result in relations such that each relation contains information about only one thing, either an entity or a relationship. A sound ER model of the database would ensure that all relations either provide facts about an entity or about a relationship, resulting in the relations that are obtained being in 2NF or 3NF. The normalization of a relation till BCNF is established using the FDs. The normalization process depends on the assumptions that 1. A set of functional dependencies is given for each relation, and 2. Each relation has a designated primary key. The normalization process proceeds in a top-down fashion by evaluating each relation against the criteria for normal forms and decomposing relations as found necessary during analysis. Therefore, normalization up to BCNF is looked upon as a process of analyzing the given relation schemas based on their condition, FDs and primary keys to achieve the desirable properties, times firstly, minimizing redundancy, and times secondly, minimizing the insertion, deletion and update anomalies. Thus, the normalization provides the database designer with 1. A formal framework for analyzing relation schemas, 2. A series of normal form tests that can be normalized to any desired degree. Decomposition through normalization should include any or both of the following properties: 1. The lossless join and non-additive join property, and 2. The dependency preservation property. Do you always normalize the database to the highest normal form? Due to performance reasons, database designers sometimes leave relations in lower normalization forms. This is called denormalization. Let us now define the normal forms in more detail. 5.5.1 The first normal form, 1NF. Let us first define 1NF. Definition: a relation table R is in 1NF if every attribute of R takes atomic values. In other words, the following conditions hold in R. 1. There are no duplicate rows or tuples in the relation. 2. Each data value stored in the relation is single-valued. 3. Entries in a column, attribute, are of the same kind, type, dot. Please note that in a 1NF relation, the order of the tuples, rows, and attributes, columns, does not matter. The first requirement above means that the relation must have a key. The key may be single attribute or composite key. It may even, possibly, contain all the columns. The first normal form defines only the basic structure of the relation and does not resolve the anomalies discussed in section 5.3. The relation student, cent enroll no, cent name, cent address, co-no, co-name, co-instructor, in office, of figure 5.3 is in 1NF. The primary key of the relation is a composite key of attributes cent enroll no and co-no. 5.5. To the second normal form, to NF, the relation of figure 5.3 is in 1NF, yet it suffers from all the anomalies. Therefore, a second normal form may be defined to overcome the anomalies. Definition: a relation is in second normal form to NF if it fulfills the following criteria, assuming the relation has only one candidate key, which is selected as the primary key of the relation. The relation fulfills the criteria of the first normal form, 1 NF, and 2. All those attributes which are not part of any primary key are fully, functionally dependent on the primary keys, key features of 2 NF times. The partial dependency will exist only if the primary key is composite. Therefore, if the primary key of a relation consists of a single attribute, then the given 1 NF relation would be into NF also, times this normal form decomposes a relation so that relations store information about one thing. Please refer to figure 5.4, which illustrates the FDs in the relation student, sent enroll no, sent name, sent address, co-no, co-name, co-instructor, in office. The FDs, as shown in figure 5.4 are sent enroll no a sent name, sent address, 1, co-no a co-name, co-instructor, 2, co-instructor a in office, 3, since, from the above FDs, you can create a FD, sent enroll no, co-no a sent name, sent address, co-name, co-instructor, in office. Therefore, the attributes sent enroll no and co-no together form the composite key to the relation student. The relation has only one candidate key, therefore, all the attributes other than sent enroll no and co-no of the relation are not part of a candidate key. These attributes are also called non-key attributes. The relation student is in 1 NF, but is it in 2 NF? No, the FDs at 1 and 2 are clearly violating the fully, functionally dependent criteria of 2 NF, figure 5.4. Therefore, the relation suffers from the anomalies as shown in figure 5.3. Next, how will you decompose the student relation to 2 NF relations? You may use FDs of 1, 2, and 3 to do so. FD 1 can be used to create a 2 NF relation consisting of these three attributes from student relation. This part new relation is student 1, sent enroll no, sent name, sent address. Similarly, you can use FD 2 to decompose the student relation further. But what about the attribute in office? You find in FD 2 that course code, co-no, attribute uniquely determines the name of instructor, refer to FD2A. Also, the FD3 means that the name of the instructor uniquely determines the office number. This can be written as, look at the screen, are these two NF relations sufficient to represent the relation student? No, as there is no common attribute between the relations. Therefore, they cannot be joined together to get the data of student relation. You must have a relation that joins the two decomposed relations. This relation would have the primary, key attributes of the student relation and any other attribute that is fully functionally dependent on this primary key. However, there is no attribute in student relation that is fully dependent on the composite primary key. Thus, you will create a third relation using the composite primary key of the student relation, as shown below, course_student, sent enroll no, co-no. Please note that the course_student relation can be joined with student 1 relation on sent enroll no attribute and with COU_INST relation on co-no attribute. The relation student in 2 NF form would be student 1, sent enroll no, sent name, sent address to NF, A. COU_INST, co-no, co-name, co-instructor. In office, to NF, B, course_student, sent enroll no, co-no, to NF, C, 5.5.3 the third normal form, 3 NF, although transforming a relation that is not into NF into a number of relations that are into NF removes many of the anomalies. it does not necessarily remove all anomalies, thus, further normalization is sometimes needed to ensure further removal of anomalies. These anomalies arise because a 2NF relation may have attributes that are not directly related to the primary key of the relation. Definition: a relation is in third normal form if it is in 2NF and every non-key attribute of the relation is non-transitively dependent on the primary key of the relation. But what is non-transitive dependence? Let A, B and C be three attributes of a relation are such that A B and B A C. From these FDs, we may derive AAC. This dependence AAC is transitive. Now, let us reconsider the relation to NF, B, COU_INST, CONO, CONAME, instruction, in office. Assume that CONAME is not unique and therefore CONO is the only candidate key. The following functional dependencies exist: CONO A co-instructor, 2, A, co-instructor A in office, 3, CONO A in office. This is transitive dependency. You had derived CONO A in office from the functional dependencies 2, A, and 3 for decomposition to 2NF. The relation is, however, not in 3NF since the attribute in office is not directly dependent on attribute CONO, but is transitively dependent on it and should, therefore, be decomposed as it has all the anomalies. The primary difficulty in the relation above is that an instructor might be responsible for several subjects, requiring one tuple for each course. Therefore, his/her office number will be repeated in each tuple. This leads to all the problems such as update, insertion, and deletion anomalies. To overcome these difficulties, you need to decompose the relation to NF, B, into the following two relations: course, CONO, CONAME, co-instructor, INST, co-instructor, in office. Please note these two relations and 2NF, A, and 2NF, C, are already in 3NF. Thus, the relation student in 3NF would be student 1, sent enroll no. Sent name, sent address, course, CONO, CONAME, co-instructor, INST, co-instructor, in office, course_student, sent enroll no, CONO. The 3NF is usually quite adequate for most relational database designs. There are, however, some situations where a relation may be in 3NF but have anomalies. For example, consider a relation student 5, sent enroll no, sent name, CONO, CONAME, dot. Assume it has the following set of FDs: sent enroll no A sent name A sent enroll no, CONO A CONAME, CONAME A CONO. Is the relation student 5 is in 3NF? The FDs of this relation can be written as sent enroll no, CONO A sent name, CONAME, sent enroll no, CONAME A sent name, CONO, sent name, CONO A sent enroll no, CONAME, sent name, CONAME A sent enroll no, CONO. Therefore, the relation student 5 has the following candidate keys: sent enroll no, CONO, sent enroll no, CONAME, sent name, CONO, sent name, CONAME. Figure 5.6 shows the functional dependency diagram for this relation. Figure 5.6, functional diagram for student 5 relation. Look at the screen. You may observe that all the attributes of student 5 relations are prime attributes as they are part of some candidate key. You may also observe that the relation has overlapping candidate keys. Therefore, no non-key attribute exists in the relation. Hence, the relation follows the criteria of 2NF and 3NF and is in 3NF. However, this relation still suffers from the three anomalies. Please make an instance for the relation, as the attributes in the non-overlapping part of the candidate key can determine each other. Therefore, the relation is to be normalized into a stronger, normal form called BCNF. 5.5.4 Boyce Codd normal form, BCNF. As stated earlier, the relation student 5, sent enroll no, sent name, CONO, CONAME, has the following candidate keys: sent enroll no, CONO, sent enroll no, CONAME, sent name, kono, sent name, coname. Since the relation has no non-key attributes, the relation is in 2NF and also in 3NF. However, the relation suffers from anomalies. Please check it yourself by making the relational instance of the student-5 relation. The difficulty in this relation is being caused by dependence within the attributes of composite candidate keys. Definition: a relation is in Boyce-Codd normal form, BCNF, if it fulfills the following criteria. I. The relation fulfills the criteria of the third normal form, 3NF, and 2. All the determinants, the left side of an FD, are the candidate key. A relation that is in 3NF and does not have overlapping candidate keys will also be in BCNF. However, if a 3NF relation have following features, then it is not in BCNF. A. It has overlapping composite candidate keys. B. The non-overlapping attributes of two candidate keys are functionally dependent. For example, in the relation student-5, the candidate keys sent and roll no, coname, and sent name, coname have non-overlapping attributes sent and roll no and sent name. Further, sent and roll no a sent name, the relation student-5, sent and roll no, sent name, kono, coname, is in 3NF, but not in BCNF. You can decompose the relation into the following relations using FD. Sent and roll no a sent name as student-6, sent and roll no, kono, coname, student name, sent and roll no, sent name. Student-6 is still not in BCNF as it has overlapping candidate keys, sent and roll no, kono, and sent and roll no, coname, and the FD kono a coname. Thus, student-6 can be decomposed using the FD as above to relations student-7. Sent and roll no, kono, student name, sent and roll no, sent name, course name, kono, coname. The following is another example of BCNF. Consider the relation enroll, sent and roll no, sent name, kono, coname, dot enrolled. Let us assume that the relation has the following FDs. We have assumed that coname are unique, sent and roll no a sent name, kono a coname a kono, sent and roll no, kono a dot enrolled. The candidate keys of the relation would be sent and roll no, kono, sent and roll no, coname. Due to dependency between the non-overlapping attributes of the candidate keys, the 3NF relation enroll is not in BCNF. This relation will have all the stated anomalies. Please draw the relational instance and check these problems. The BCNF decomposition of the relation would be stud1, sent and roll no, sent name, COU1, kono, coname, enroll 1, sent and roll no, kono, dot enrolled. You now have a relation that only has information about students, another only about subjects, and the third only about relationship enrolls. Higher normal forms. Are there more normal forms beyond BCNF? Yes. However, these normal forms are not based on the concept of functional dependence. Further normalization is needed if the relation has multi-valued, joint dependencies, etc. These are discussed in Unit 6, 5.6 Desirable Properties of Decomposition. In the previous section, you have learnt the process of normalization using functional dependency. Normalizing a relation entails decomposing a relation into a number of non-disjoint projections of the relation based on the FDs so that the three anomalies are minimized. But why are these projections non-disjoint? The non-disjoint relations allow reconstruction of the original relation instance through join operation. In this section, we discuss about the properties of the good decomposition. The decomposition of a relation should fulfill the following: attribute preservation. All the attributes of the relation which is being decomposed should be part of at least one of the decomposed relations. This is a necessary condition, otherwise the decomposition will be lossy. Lossless join decomposition. For explaining the concept of lossless join decomposition, let us first explain a lossy decomposition with the help of an example. This example also explains why FDs should be used to perform proper decomposition of a relation. Example, consider the following instance of a student 9 relation. Student 9, sent enroll no, co-no, dut enrolled, co-instructor, in room, with the following set of FDs, sent enroll no, co-no a dut enrolled, co-no a co-instructor, co-instructor a in room. Suppose you decompose the student 9 relation randomly into two relations sent 1 and sent 2 as follows. Sent 1, sent enroll no, co-no, dut enrolled, co-instructor, sent 2, sent enroll no, in room. Are there problems with this decomposition? Yes, but for the time being, let us focus on the question whether this decomposition is lossless. Consider the following instance of the relation student 9, sent enroll no cono dut enroll co-instructor in room 1001 MCS to 01 1st February 2022 Preeti 1. 1001 MCS to 02 1st February 2022 Salim 2. 1002 MCS to 01 13th February 2022 Preeti 1. 1002 MCS to 03 13th February 2022 Shashi 3. 1003 MCS to 0 to 15th February 2022 Salim 2. Figure 5.7. An instance of student 9 relation. The decomposed relations sent 1 and sent 2 would be sent 1, sent enroll no cono dut enroll co-instructor, 1001 MCS to 01 1st February 2022 Preeti, 1001 MCS to 02 1st February 2022 Salim, 1002 MCS to 01 13th February 2022 Preeti, 1002 MCS to 03 13th February 2022 Shashi, 1003 MCS to 0 to 15th February 2022 Salim, sent 2, sent enroll no in room, 10011, 10012, 10021, 10023, 10032.